Acids can furnish more than one proton if they are polyprotic, diprotic, or triprotic. Here are some examples. But they always dissociate in a stepwise manner. So that means one proton at a time. So this will happen in two separate chemical reactions. And successive K values can be given, right, for the dissociation of the various hydrogens. So down here in the table, you can kind of see here are several polyprotic acids and the K, the equilibrium constant that expresses the products over reactants when the first hydrogen comes off, the second hydrogen, and the third hydrogen. Right, this one only has two hydrogens, so there are only two Ka values. This is a strong acid, so its first Ka value is actually too large to measure with certainty, but the second Ka value is that. One thing I want you to notice about these is that the Ka values for the first hydrogen are relatively large, -3, -7, -2. Then they get smaller, -8, -7, -11, and even smaller, -13, -12. So what does that tell us? A large Ka value means that it favors products, right? The equilibrium lies to the right of the arrow. This is likely going to happen. So for each one of these acids, they are likely going to give off the first hydrogen. They're less likely to give off the second hydrogen and even less likely to give off the third hydrogen if that were to happen. So you'll see they're lower, that's what this says, and we can calculate pH normally for the first dissociation, but then we'll use the successive concentrations that we get to find the new. So here's a sample problem similar to tonight's homework where we're going to use all of those facts. So here we have a polyprotic acid, see it has three hydrogens. The Ka for all three of the possible chemical reactions that could occur. And then they want us to find the H concentration, OH, and the concentrations of all the intermediates. Now, one thing I want you to understand is this acid is being put into a solution. The first hydrogen is coming off, and then potentially the second. So the second will be added to the concentration of the first, and then the third would be added to the concentration of the first and the second. So we will be doing the same math we've been doing, but the extra step will just be to remember to add anything new that it comes off, anything new that dissociates with anything that has previously dissociated. So this does require some steps. And I'm just going to call this first step, step 1. And the chemical reaction for step 1 starts with dissociating into, and of course, remember to put a minus sign, right? And they tell us the concentration of the original acid is what? 0.2. So let me write that down. Now, I do not know the concentrations of the other substances. Do I? No, but I can figure those out with the same methods we've been using. So remember, products over reactants. The two products here are H plus and the anion that came off. So since they're in a 1-to-1 ratio, this will be x squared in the numerator. And then the only reactant is the original acid. And I know its concentration is 0.2, but some of it will dissociate, so that's the minus x part, remember? So I've got these concentrations and that concentration. All right, I also have the Ka value, so let me plug that in. And notice I'm using the Ka1 because it's the first hydrogen that we're dealing with. So when I go through the steps of calculating this first acid coming off, I happen to know that this method fails the 5% rule. So I'm going to have to put it into a quadratic equation in my calculator. Remember that in order to put it in a quadratic equation, it has to be in the format ax squared, bx, and c. So the value for A here is just 1 because there is no number in front of the x squared. The value for B is 5.5 e negative 3, and the value for C is negative 1.1. These all have to be plus symbols in the middle. So I went ahead and did that, and x for this one is. Now, I always like to ask myself, what am I solving for? What does this x represent? Let's go up a step and see what it represented. X here represented these two products, and the one we often care the most about is the hydrogen, but this time we're being asked to find the concentration of everything. So let's just write it down. For hydrogen, we know that it is, that is the same here. And then for the original acid, some of it has been used up. Remember, we subtracted. So just right here, I'm just going to show the subtraction. You could do the math later. Okay, so I have my first 3 concentrations. Step 2 is that the anion that still contains hydrogens will now dissociate in the same solution. So we're going to have H2 dissociating into some H ions, and notice that the charge continues to get more and more negative as it releases hydrogen ions. All right, I'm going to do the exact same work. I'm going to set up a Ka expression. This time I'll use Ka2, and I've got my 2 products, which are H and the anion, but be careful here. There's already some H, so I shouldn't just write X. I should write the known concentration. And there will be more hydrogen released through the series of this reaction as well. So it's the previous concentration of hydrogen plus this. And did we have any H? No, this is brand new, so we don't have any HASO4 yet. And how about H2? We had some. This is the one that's actually dissociating right now, so I'm going to put minus X. Now, if you didn't follow the logic of those very well, it's because you need an ice table. And don't be afraid to just jot one quickly in the corner where you can write down the initial concentrations. Those would be these things here. And then you can write down the equilibrium concentrations, and that's these expressions here. We're showing that we know that the original H, right, is going to add some X. The original H2SO4 is going to lose, right, some hydrogens. And we do not know anything about this new species yet. But that's how we came up with those 3 expressions. Let's go ahead and solve. We're going to ignore these because they are small, and we're just going to calculate X. And this works even more reliably for a polyprotic than it did before. I know you might have felt, well, hey, we don't know if it passes the 5% rule. The first hydrogen didn't pass the 5% rule, but successive hydrogens for a weak acid will almost always pass the 5% rule, and it helps to make the math so much quicker. Check this out. We've got the exact same number in the numerator and denominator, so it's really just X equals, again, what is X? So I need to put molarity, right? And I can go back up and write down all of the numbers that I have so far. So the original amount of acid, that is not changing, but the hydrogen has changed. Check this out. It is the 3.1 from before and the 1.7 from current. So when you add those 2 numbers together, that'll be the new hydrogen ion concentration. And then for this last substance, that is the concentration there. And for the first substance, remember, we were subtracting. So it's going to be 3.1 minus. Okay, time we're starting with and releasing. Okay. We're going to write our K expression. Can I just go ahead and plug in K? Again, it's not okay for us to use the x squared in the numerator this time. We already have some hydrogen. It's whatever this number was from before. What is this number from before? Let's see if I've written it down. I didn't, so I'll put the whole thing in here. Okay, and we'll crunch the numbers later. I'm trying to make this video quickly since I know you are not going to be in class today, and we certainly will miss you. And then what about the ASO4? We have that from the previous. And some of it will be lost. So we're using the same logic here. We're going to go ahead and ignore these x's. I'm sorry, there should be a plus x here. Isn't just a tiny bit more hydrogen going to be released this time? Absolutely. A little more hydrogen coming from this last one. We're going to ignore because they're small. And that's almost always the case for polyprotics, that once you get past that first hydrogen, they are small. So I went ahead and plugged this in my calculator so we could move kind of quickly, but please plug it in yours so you feel confident about this. -17? That's a super small number. And this again represents the additional hydrogen. So I'll put molarity here. Now, I finally know how much hydrogen there is. It's all three of these numbers added together. There's all three of the numbers here. And then this last substance, it's just the little bit that's been produced, 17. So let me go back and make sure that we've solved for everything. We finally got that H. Ooh, feels good. And we have these two things as well. OH is the only thing we do not know, but we can easily find OH concentration if we know H concentration, right? Because H times OH equals, right, 1 times 10 to the -7, the ion product constant for water, ion concentration. So you can get that number. That's pretty easy. So that's it.